So in the but in the 3D case, it's the same. We want a way to define for arbitrary loading histories. Okay, we want a framework for which we can solve plasticity problems and determine when something's yielding, apply a flow rule, and do it for arbitrary loading histories, right? So we'll look at the case here of an isotropic hardening material. So in, in an isotropic hardening material, after the yield point, which would be defined here, then you have the material hardens with some slope h, okay? And so now your yield function has to be a function of something else. So before we had that the square root of 3j2 is minus y, right? That was our yield function. But now y needs to be a function of something, and the function that we're going to make it of is something called the equivalent plastic strain. Okay? It's going to be a function of the equivalent plastic strain, and that's going to be equal to 0. Okay? And specifically for isotropic hardening, what that function will look like will be square root of 3j2 minus y minus h epsilon p, right? So you can see that the hardening is going to be proportional to the equivalent plastic strain. Okay, and remember this yield functional, it's a scalar, right? So the equivalent plastic strain is a scalar thing. And this is that internal state variable. So this is an internal state variable that we use to describe all of the plasticity mechanisms that are occurring, right? And so the way we define the equivalent plastic strain, obviously we need, if we're going to use it in this yield functional to decide if the material is yielding or not, we need to have a definition for it. And the definition for it, we actually define it in terms of the equivalent plastic strain rate, okay? And it is the square root of 2/3 the equivalent plastic, the plastic strain, epsilon ij, right? So epsilon ij, that's the plastic strain tensor, okay? And if I contract the two tensors together, then I get a scalar. And the square root of 2/3 comes about for the very same reason that for the equivalent stress it came about, right? If you remember, there was a square root of 3/2 in that one. Okay, so this is the definition of equivalent plastic strain. Right? And if we plug in our flow rule, remember we have a flow rule that says that the plastic strain rate, this is strain rate, by the way, strain rate. So then the equivalent plastic strain is the integral from 0 to some time of interest of the equivalent plastic strain rate dt, right? So our definition is in terms of rate. If we want to get the equivalent plastic strain, we have to integrate this guy. Right? So then we also have the flow rule, right? So our flow rule, our associated flow rule, says that the plastic strain tensor, strain rate tensor, is equal to lambda dot, and now I'm going to use the normalized definition, so Sij over the magnitude of Sij, and I'm going to call this thing here Qij. So it's just a unit tensor in the direction of the deviatoric strain. Okay? And so then if I plug this into this equation, the one I get is the square root of 2/3 lambda dot. The reason is, right, I plug in lambda dot qij, so I have lambda dot qij, lambda dot qij, so I have lambda dot squared. And then the contraction of a unit tensor, qij with itself, just gives me 1. So then I have the square root of 2/3 over lambda dot squared, take the square root, sign off the lambda dot. Okay, so the next thing is, because we assumed that for J2 plasticity, the deformation is isochoric, right? It's volume preserving. In other words, any plasticity only comes about because of deviatoric motion, because of deviatoric strain. And because of that, we can build this framework we're working on here all in terms of deviatoric quantities. We don't even need to mess with the isotropic quantities, right? So I'm going to define, or we're going to work with the deviatoric strain. So I'm going to put a little d there for deviatoric strain. And of course, we know that the deviatoric, just like the deviatoric stress, the deviatoric strain is the total strain minus 1/3 the volumetric strain, or the dilatation, right? And so we're going to work in this deviatoric framework, and our additive decomposition of strain rates also holds in terms of just the deviatoric components. You can actually work it out and show that it does, but I'll just write it down. So we have that the total deviatoric strain is equal to the deviatoric elastic part plus the deviatoric plastic part. And these are rates, right? The decomposition holds for rates. And I'm just going to rearrange this equation. Just going to move everything to one side. No big deal. And then I'm going to multiply this equation on the right by qij. Now I have a scalar equation, right? I had tensors, but now these are contracted, so these are scalars, right? And it'll be a little more clear. These will reduce down even further some of these terms, but clearly this is a scalar equation. So I'm going to go to a new page, but we're going to come back to this guy. So I just want to point out, remember we write down Hooke's law like this? For an isotropic material. right? And we just said the deviatoric strain is equal to the total strain minus 1/3 sigma kk delta ij. Well, let's solve this equation for the total strain. So then I have the total strain is equal to the deviatoric strain plus 1/3 sigma kk sigma ij. All right. So let's plug this in up here. Okay. So if we do that, we have lambda sigma kk delta ij plus 2 mu deviatoric plus 1/3. So if we distribute the 2 mu, then and just rearrange the equation, I have this. Does anyone know what this is? Probably not in your notes, I think, because but you remember I said that there's relationships between all the elastic constants, right? And if you go to Wikipedia, you can look at a big table and it shows the relationships. Well, one of those relationships turns out to be really nice, is that this is K. It's the bulk modulus. So I can alternatively write this equation as 2 mu the deviatoric plus sigma kk sigma ij k. Right? So this is another way to write Hooke's law. It's just now you have 2 mu times the deviatoric part, right? Okay. So let's look at so then we also know that Sij is equal to sigma ij minus 1/3 sigma kk delta ij. Well, let's evaluate this equation at sigma kk. Right. So at sigma kk, I have 2 mu, or let's say ii. So 2 mu ii sigma, the deviatoric strain plus sigma kk ii times k, right? Well, the trace of the, epsilon ii is the trace of the deviatoric strain tensor. What is that? 0 by definition, right? What is the Kronecker delta function ii? It's 3. So I have that sigma ii is equal to 3k sigma kk. Okay, so let's plug now this into this equation. So I have that Sij is equal to, this term is going to come from here, so 2 mu ij plus sigma kk ij. Now this term, where I'm plugging in, sigma kk is 3k epsilon kk, right? So I have plus 1/3 times 3k, k here, k epsilon kk j. All right, well, these terms cancel, right? So then finally, all that to say that Sij is equal to 2 mu. So the deviatoric stress, elastic, right? This is elastic, if it's not clear. because it's Hooke's law, right? It's all elastic. So that might have been obvious by inspection, but I just wanted to go through all the details there. So the deviatoric stress, the elastic part of the deviatoric stress is 2 mu times the elastic deviatoric strain. Probably obvious by inspection, but just wanted to go through it. All right. Okay. So we had this equation, the one I said we'd come back to. Okay. Well, we just solved for, remember, so we just said that Sij is equal to 2 mu epsilon deviatoric Ij. So we can solve this guy for epsilon like that, right? So now, yeah. Yeah. Take the time derivative of both sides of the equation, right? All right. So now I have something here that I can plug in there. And this comes from my flow rule, right? So I can plug that in there. And so then I have an equation like that. Because I plugged this in there, right? So then I have lambda dot qij times qij, which gives me 1. So it just leaves behind the lambda dot. Right? I'm also just going to define this guy. This is clearly a scalar, right? It's Sij qij. We're going to show that you can show that that's just something S dot, right? We'll define it as S dot. So this is not a tensor, but like the scalar deviatoric rate. Right? So finally, you have that. And this equation, we'll call it star. It's kind of special. We'll come back and use it later. So for the specific example, it turns out that this equation will be applicable to more types of plasticity. But for this specific example of isotropic hardening, which we started to discuss earlier, and the reason I call it isotropic hardening is that what we're talking about here is that in our stress space. That's supposed to be a circle. But in an isotropic hardening model, as we strain it, as the equivalent plastic strain evolves, this circle gets bigger. And that's opposed to, there's another type of hardening called kinematic hardening. So in a kinematic hardening, the circle would actually translate into stress space. So you could imagine that it moves this way due to some evolutionary law. And so kinematic hardening, it might be easy to see that kinematic hardening introduces deformation-induced anisotropy. Right? So if I'm the same distance from the origin here, I'm elastic because the yield surface is translated in stress space, and now I'm inside of it, right? So I'm elastic. But if I'm the same distance in the opposite direction over here, now I'm clearly outside that red circle. Even though I'm the same distance from the origin, I'm clearly outside the red circle, which means I'm plastic, and I'd have to return myself to the yield circle. Right? So that's kinematic hardening. This is kinematic hardening. Rocks, by the way, exhibit this type of hardening behavior, kinematic. But right now, we're just talking about isotropic. So in isotropic hardening, as I accumulate equivalent plastic strain, the yield surface grows. And this makes sense if you just look at what an isotropic hardening model looks like in a stress-strain curve, right? So we have stress, strain, right? So if I load the material, I pass the yield point, and I start to harden. If I unload, right, I come down here. Well, now you notice if I reload, I follow this line back up. Now I don't yield again. I have elastic deformation up until this new point, right? So this is like y new, whereas this is y old, right? And see, y new is larger than y old. So the yield surface grew, right? So then, again, our yield surface is square root of 3j2 minus y minus h epsilon p, okay? And what we're going to do is we're going to solve an optimization problem, essentially. And if you've ever had a class in optimization, you might be familiar with the Kuhn-Tucker constraint conditions. And those are that f is less than or equal to 0, lambda dot is greater than or equal to 0, and lambda dot f is always identically equal to 0. And those then lead to a complementary condition that f dot must equal 0. Right? So if we compute f dot, so this is f, right? Compute f dot for that thing. We're going to have that the square root of 3 half s dot minus h epsilon dot p is equal to 0. And then if we plug in our definition for epsilon p, we have that the square root of 3 half s dot minus h times the square root of 2/3 lambda dot is equal to 0, okay? And we can solve that equation for s dot is equal to 2/3 h lambda dot. And then we'll plug that back into star. And then we have an equation that the only unknown is lambda dot, and we can solve for it. So if we do that, we get that lambda dot is equal to this. So then, returning to our additive decomposition of rates, we have that the total deviatoric elastic is equal to the total minus the plastic, right? Which is equal to the total strain rate. And we have a flow rule, right? So we have a flow rule that's like lambda dot qij, right? And that's equal to that. We have an expression for lambda dot, so if we plug that in, right, then we have total strain rate times 1 minus h over 3 mu plus 1. You could simplify this. I didn't. Right? So now we have an expression for the elastic strain rate. So the elastic strain rate is equal to this. And so that's, if, I guess I should say, if it's yielding, which means if F equals to 0. Right? So if it's plastically deforming, then you have this. Keep in mind that the total deviatoric strain rate tensor is something you know. I mean, it's what's driving the problem, right? We take a step and we equilibrate. We have displacements. We compute strains. We can compute the deviatoric strain, right? And that's the total deviatoric strain, right? Okay. So now we have an expression for the elastic strain in terms of the total strain plus some other things, or times some other things, if it's yielding. And so then we can just plug this back into Hooke's law, right? In the rate form, right? So we have that the stress is equal to 2 mu times the deviatoric elastic times this guy, right? Almost out of time, so I'll just say that the stress is equal to, it simplifies to 2h mu h plus 3 mu So now we have a way to update the stress. Right? So we basically have to check to see if we're yielding. If we're not, if our yield function is less than 0, then we just update it elastically, right? If it's not, if this is not less than 0, then it's plastic. It has to be identically equal to 0. The lambda dot enforces that. In this case, we can eliminate the lambda dot explicitly from the equations, so we can write what the new stress is under plastic deformation. And for this case of isotropic hardening is really the only time you can, it's one of the only times you can ever write it down explicitly like that. You can explicitly eliminate that lambda dot. For any kind of more complicated material, which we're going to move on to talk about, say materials that, so isotropic hardening is like this, but you could have materials that harden as a function of strain rate. So this is a pretty common behavior. So as the strain rate, as the plastic strain rate increases, the material gets harder. And in these scenarios, you can't solve for lambda dot explicitly like that. You have to actually, what you get is an equation that's nonlinear in lambda dot, and you have to do a local Newton iteration, a local nonlinear solve to find out what lambda dot is, and then you plug it back into the equation. So you have to actually numerically solve for lambda dot in order to update the stress. Okay. And so we'll talk about an example of that. The nice thing is, I know it was kind of maybe a little bit wonky, but the framework is general enough such that, that equation star, it applies no matter what, if you can use that equation along with, a yield, your specific yield function to the plasticity model. Those two things can be solved together for lambda dot, no matter how complicated the actual yield function is. Okay, so you can solve them together, at least numerically, you can always solve them for lambda dot, and then you can update the stress accordingly. Okay?